All right, so okay, so we have been dealing with shear flows in panel. Okay, and every single model we have done, the panels were basically rectangular. And if you look at the structure of an aircraft, you will see that probably the vast majority of panels have a rectangular shape, no, on the wing or the fuselage. All right, but in some cases, those panels cannot be rectangular and can be actually tapered. So we're going to see what happens when the panels are tapered and not rectangular. So let's say in most cases, aircraft panels are rectangular, but in some instances, the panels are tapered. Okay, so basically what is it? This is a rectangular panel. And this will be a taper panel. So we have see here that Q okay, we have been assuming that we have a constant value. But what could happen if the panel is tapered? Is that now the Q's can be non-constant. Okay, so probably for the next, whatever, 20 minutes, I'm going to go through a derivation on showing how to find the shear for a taper structure. All right. Again, the derivation is not that important, but what's important actually is that the final equations, okay? So if you get a bit lost, don't worry about it. So let's over here. Let's analyze the taper panel. Okay, I'm going to use some nomenclature. So S stands for short, L for long, capital B for bottom, and T for top. Okay, so now I'm going to do a figure here. Okay, so let's say it's right here. Okay, so Y, X. So we'll be calling here this H long. This one over here, short. This one will be theta top, and this one will be theta bottom. this distance will be X short. This will be the length of the panel, L. And this distance right here would be X long. Okay, so I'm gonna say here, assuming that all shear flows are constant along the edges. So what does that mean? Is that along each one of the edges, so QL will be constant, Q sub S will be constant, Q top will be constant, and Q bottom will be constant. Each one of them will be constant. Okay, so if you look at the top figure, we do summation of forces along the x equal to 0, you're gonna get that Q top times L cosine theta t times cosine theta t minus QB L over cosine theta bottom cosine bottom equal to 0. So this is only going to give the equation Q top times L minus Q bottom times L equal to 0. So this equation is only valid if what? If Q top equal Q bottom, and let's just call this one Q hat. All right, so now we do the same thing for summation of forces on the Y.
Did you show that possible grade 1 more?
We do the same thing, summation of, like I told you, the deviation is not that important, but since you don't have a book, this is gonna give us what? Minus Q sub S, H sub S. That's why I don't go that much in detail. I show you where is each term coming from because I don't really care that much. Okay, plus Q top. Q B. Okay, so over here we just say that the Q top and the Q bottom is equal to Q hat. And if we carry a little bit the algebra, we get Q sub L, H sub L, minus Q sub S, H sub S, plus Q hat L tangent theta t minus q hat L tangent theta bottom equal to 0, which gives q lower equal to q short h sub s over h sub L minus q hat of L tangent theta top minus L tangent theta bottom. And this over here could be shown to be equal to h sub L minus h sub S over h sub L. Again, all these stuffs come from basic trigonometry, summation of forces, and so on. But again, I'm not spending too much showing the derivation. So this will give you q sub L equal to q sub S, h sub S, h sub L minus q hat h sub L minus h sub S over h sub S.
You said it was over.
The which one? Oh, wait, let's see. You're right, h sub L. Was that your comment?
Yeah.
Yeah, you're right. And this would be equation A. Okay, so next. So we have our taper again, but this time this is our point A over here. So if you want, we have here Q long, Q short, Q, oops, and Q hat. Forget about the outside one. So we do summation of forces on the X, summation of forces on the Y, and finally we do summation of moments about point A. Counterclockwise positive. And this is gonna give us Q long, H long times L minus Q hat L over cosine theta T cosine theta T H sub S equal to 0, which simplifies to Q sub L H sub L times L minus Q hat H sub S L equal to 0. Or we can solve it here, Q sub hat will be equal to Q sub L H sub L H sub S. And this will be our equation B. Next, I write substituting B into A. We get Q sub L, so B sub A is B sub A is what? Q sub L equal Q sub S, H sub S, H long minus Q hat, HL minus HS. Let me not do the mistake. H sub L. If I substitute, I get Q sub S, H sub S, H sub L minus Q hat is QL, HL, H sub S times H sub L minus H sub S over H sub L. Okay, if you factor out the Q sub L, we get this will be equal to, sorry, the Q sub S, we get Q sub S okay, of H sub S over H sub L squared.
Would you mind moving the paper up just a little bit?
Yeah, I do that right now. Hold on 1 second.
Thank you.
Yeah, no problem. Okay, and now we do page 3. Substituting C into B, we get Q hat equal to QL, H sub L, H sub S. Q hat would be equal to Q sub S, H sub S, H sub L square times H sub L over H sub S. So basically we're gonna have Q hat equal to Q sub S, H sub S over H sub L. Okay, so basically we did the derivation, all this part of the derivation, I'm not that concerned. All I want you to write down on a piece of paper, the important information comes now. So I'm gonna put that here in summary. If Q sub S is the known shear flow, okay, so let's say this is our taper final, Q long, Q short is known, Q top equal Q hat. Q bottom equal Q hat. What do we have? So QS stay unchanged because it's known. And now Q long will be equal to what? Will be equal to QS H sub S over H sub long square. And then this will be still Q hat. Q hat and Q hat is equal to what? To Q sub S, H sub S over H sub L. So that's basically what I want you to use over here. You don't need to memorize it, okay? I write it down. But this will be it, okay? Again, the derivation is not that important. Actually, there's different ways to do the derivation of this because actually this equation here is only valid. I didn't put that at the beginning. But if the taper here, if this angle over here is kind of small, okay? If it's large, everything changes quite a lot, okay? But you need to have some type of approximations, all right? And everything gets a lot more complicated. All right, so let's take like a few seconds rest and let's do one example.
Out of curiosity, what kind of small angles that normally held to? Like,
Small angle jellies on application is considered between, if you want, so 0 or 1 and 7. Okay, so it's like the small angle assumptions. Okay. All right, so let's look at one example. All right, so let's see one example here. All right. So let's see, this is our panel. So this is what I have over here. Here we go. 1, 2, 3, 1, 2, 3, 4, okay. So this one is simply supported here. Here we have a roller. This will be 0.1, 2, 3, and 4. Okay, we know the length of the panel to be 1 meter. This angle over here is 15 degrees. We apply vertical force of 5,000 newtons going down at 0.3. The short H sub S will measure 0.45 meters. And the long over here measures H sub L 0.6 meters. Okay, the question here is to determine the shear flows in the taper panel. Okay, and because we're gonna be doing the final element, and personally, we always have problem with that, with the trigonometry. So let's see the coordinates of this point. So let's say of point 1 is 0, 0. Coordinates of point 2 will be 0, negative 0.6, 0.3, 1, negative 0.717949, and 0.4, 1, negative 0.267949. Sorry? Yeah, we use that for FEMA to create the points. That will be used for FEMA. Okay, you want to put here FEMA. Okay, so let's say here we can say like from the figure, okay, and if you compare to this data over here, okay, over here, all right. Okay, what can we say? We can say that Q12 will be Q long, Q34 will be Q short or Q43, whatever you want. Then Q14 will be Q top, which will be Q hat. And Q23 will be equal to Q sub B, which again will be Q hat. Okay, so if I kind of redo the figure, let me redo the figure since I'm not able to show both figures. So let's see, I'm gonna have over here then. Okay, so I have here. So now on this side, you have Q short. Q long. Q hat. Q hat. And we also had the equation from before that Q hat is equal to what? Q sub short, H short, HL. And that Q long will be equal to Q short, H sub S over H sub L squared. Okay, so let's see, how can we find Q sub S, the shear flow along the member 3-4? What have we been doing so far all the time? What could we do? We could just go and say, consider the vertical member 3-4, no? And see what happened. Because remember, over here, like always, this will be, here is a panel, and this will be longerons, stiffeners, or stiffener, longerons, or flanges, okay? All right, so what can we do? Can just go and say, considering member 3-4, then what do we have? So here, it's a figure of 3-4. Let's see, 4 here, 3 over here. We're gonna have the 5,000. We know this will be a 1/4 member. Q sub S. This is A short is 0.45. So now, in order to determine Q sub S, what can I do? I can do summation of forces on the vertical direction, or if you want, on the y direction. And this will give what? Q sub S times H sub S minus 5,000 equal to 0, which will give Q sub S equal to 5,000 divided by H sub S. So it will be 5,000 divided by 0.45. And this will give you the Q sub S equal to 11,111 Newton meters. Okay, and next, using the relations. One thing for you guys here there, if you ever come to my office or sometime, I'm going to ask you to show me your class notes. Okay? And doesn't count to print my class notes, okay? From online. All right. I think I already mentioned that. I tell you, I have more than 20 years experience on this. The students are as good as the class notes are. The reason is very simple. You study from what? From your class notes, no? So if your class notes are not clear, there's no way for you to study properly the material. Okay? I don't know if that makes sense or not, but I think to me it makes sense. All right, so I try to show you. Anyway, so using the relation from the previous page. So basically, I mean, these two relations over here. Let's see, we have Q long equal Q short H sub S over H sub L long. So this will be equal to, so if you do the calculation, this gives you Q sub long equal to 6,249.94 newtons per meter. And Q hat is equal to what? Q short H sub S H sub L, which will give you Q hat approximately equal to 8,333.25 Newton meters. Okay, so in summary, what do we have? 4, 3. So at the end, I will have this is equal to Q S 11,111. Q top equal Q hat. Oops. $8,333.25. Q bottom equal Q hat equal to 8,333.25. And Q long equal to 6,249.94. Okay, so next I'm going to give you some time, but basically using these things, these coordinates for the FEMAP, I want you to work on the FEMAP on your own and see if you can validate this, okay? I'll give you about 20 minutes and then I will do it very quick and let's see if we can compare the results. So I'm going to pause the video here. Open FEMAP and let's see if you can do it on your own, all right? Yeah, I think you should be able to do it. I don't even think you need the 20 minutes, but.
Did you ever say we're considering the periphery to be rods or just? Yeah.
He's not.
It is just straight up panel?
No, it's just a family. But
You better.
made the geometry and then what to do. It's after put down the lines where we go.
So you don't have to do that, you can go to geometry. surface, and then you can use the points to create a surface instead of having to do the lines all the way around. It's nice, there's no, model, is name. All the time. He likes to use a little bit of border. So I think these verbs, I was gonna be. There was no.
So after surface.
I'm on this step too. So the top one is fixed, yes. And so, yes. My model, you have a transparency of the systems. So. And that's when we,
I'm trying to remember what the.
it's translation of what, no TX, something like. No.
Could be
One to lower.
modeled and material, right?
Yeah. So. You want to be able to translation.
Probably.
Oh, it's translation.
So I would go for.
Right, rotation, is that what that is? Yes, we're not rotating to the translation, so translation line. Yes, it should be this, right? No, it's able to Z. All three one. Then, this is the perfect. I see what you're doing. What?
Which of them has you been using?
White word.
Yeah. Loads.
So this one, we choose the fix.
Technically, the top is fixed, it's just needed to, it's big.
No, you said this fix, this is in fix. Yeah, okay, so then. This one,
Yeah.
this selects, this is right, this selects, okay, so. It worked from the screen into just TY.
We're talking about. No. This thing.
So it's 3.9, you see that. Country. Easy. Yeah. Oh, One. Yeah, that's factor, and then all, yeah.
Segments of.
No, it's another role.
I know, it's got to wait till like. Okay, well, I guess pin on this list, pin, no translations.
Yeah, so for the constraints, you go model, constraint.
I know.
One.
Yeah.
How do you do constraints on that?
But for the rollers, we don't need to.
I just selected it to be, so how are you doing constraints, are you on through?
I just go through model and on point, yeah, just get it rid of.
The same.
Model constraint on 20, okay, so then. You click the one you want, hit okay,
Well, I know that.
and then
We'll
arbitrary,
pick.
in advanced types. Underneath the standard types and advanced types. What we're doing is we're selecting translation of Y, because this is a roller, it can only go up and down technically. And leaving it like that, so I'll think it's.
So it's geometry. It's okay.
Okay.
Technically, we could do no rotation, but I'm not sure about that. So now we go to the mesh control. Okay. The size on surface, we click that, hit okay. Element size, it's gonna be just 0.1. What? Yeah.
Every quarter week.
We did. No. Okay.
You just.
So you're good.
Yeah. And here's the, I don't know how it is. Do you have storm, can you zoom back where actually, we have the mesh,
Yeah.
so we have the inputs, we don't like. We. Yeah.
So the mesh size should be.
Geometry.
Jump for the
Mesh. Geometry. So it's.
Is it also select the little, yeah, it's a negative. It's really just the.
Okay. But we can do it next week, though. Looks like this.
But you're okay.
Yeah.
Yeah, that's just, yeah. But. Now it was, we're supposed to check if there's no, citizens. Trees. How do we?
Tools, check.
What's the points? No, it's other time. And then John 3. It's not on. Analysis. No. D1. Which analysis type should we be doing?
Static.
So.
And I got an error message.
I tell you, you need to pray before you click that stuff.
It's Frank's point nine.
Did you apply the boundary conditions? Did you apply the boundary conditions?
No, no.
So that's probably what it is. If you don't put stuff, it's probably boundary conditions.
We need my boundary conditions.
The simplest supporter and the roller.
I put that, I put those under constraints.
Okay, so Johnny, Johnny, that errors comes from that. Anyway, keep working on it. I want you to struggle a little bit. You should not be struggling, and then we do it together, okay? You'll have about 10 more minutes.
No.
Model node. Oh, we have points on node. So when we first start making the panel, should we do it with points or nodes? Because it came up with a fatal error that say no nodes are points.
I will make points and then lines, or you can do a surface from the 4 points.
Yeah, we did the surface,
But keep struggling a little bit, struggling, you're gonna learn, and then we do it together, okay? Still have 10 minutes. It's not that I don't want to do it, but if I do it right away, you're just gonna get used to, okay, I just see what he's doing and sometimes I get error as well. I'm telling you, I never know why, but sometimes I get errors, I don't know why, and the best option many times is just to start from zero, so.
Right.
That's what I tell you, a little prayer sometimes goes a long way.
Wait, hold up. Here, it has a failure.
Alright.
Which one's good line?
Oh, we don't.
Nothing on the one.
Yeah.
Yeah, no, it depends what's the. Facilities. Oh, you make them down. Or the difference. And typically, you know, really go by the law of that. I believe if, well, if it would be, but then I'm going to say, height. And then it is, and it is like. So it's.
You could also just go into the file and put it, we just say that.
Okay, and then cancel. And then you go to model. This, you're gonna do a shear panel, 10 times. And then material.
How's yours threaded? Mine didn't do that.
When you go through, when you make the mesh, or not the mesh, you make the spacing. For your elements. So if you go to model, or not model, you go to mesh. And then geometry and surface. You can then select the entire surface. Then you should do a spacing like 0.1, so that's what we did beforehand.
I mean, do you create a shear panels? Yes, no?
Yeah.
One fatal error in it. Doesn't even tell me what fatal error it is.
Yeah, no, this is not that's not actually.
No, Leslie, you could actually tell me what the fatal error was. What are they gonna be wrong about?
You know, I don't.
Say this. Yeah.
Yeah.
What results? Oh. I see what it is.
Solution for the residual structure in the parenthesis of case does not exist. What? What does that mean? I think I'm stupid.
So we're supposed to be doing rods on periphery, right?
Yeah, just like the same way I've been doing.
That's what we can.
Didn't do what?
Rods. The rod from.
What do you mean?
Feeling 3 per one. Fair funds. Then you do. Need to be. Model.
All right, so I'm gonna do it. All right, so let's see. We do need to go here. Resume. So probably you have done this part of it. So geometry points, help me over here, 0, 0, 0. Negative 0.6. Then I go to 1. Negative 0.2679949. And negative 0.71, 7949. Okay, cancel, Control A. I get those 4 points, geometry, surface, corners, methods, on point. Select this one, this one, this one, and this one. I go to model, material, whatever, I can put here 73.1 to the 9. It doesn't matter what you put here, you could put 1, it will not change anything. But this is for the aluminum 2024, basically. Okay. Cancel. Now mesh control, size along surface. I don't know, how long is this stuff? 1. So maybe put here 0.25, I don't know, how would that look like? Too big? So select all, 0.25. You can do 0.25, but let's say divided by 4. Okay, that looks a little bit better. Just one thing here. Let's look at how many elements do we have over here? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, so did I count it 10 and 10? Yeah. Okay. Anyway, if I run into the mistake, just want to make sure the same number of elements at the top and the bottom. So maybe let's do this. Mesh control, size along curve. Select all the curves. And now maybe say number of elements. Okay, this will go. Let's say 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay. Maybe let's change that to, let's leave it like that. 10. That's fine. Okay, the reason that I want the same number of elements at the top and the bottom is to see that we can make like this kind of squares, no? But if you don't have the same mesh size, it might do like weird elements. So now we go to properties, new. Let's select the material. Let's first do the one of the shear panels. Here I always tell you to put a small value. Here, let's say I put 1 millimeter. You can put 1. It's going to change a bit the result, but not much. Okay, cancel. Activate this one. Mesh geometry surface. What am I missing here? Maybe I'm small values, F1, F2, F3, F4. Here you can put 1 and just put something that is more realistic, like 1 millimeter instead of 1 meter thickness, no? Okay. Mesh geometry surface. Select that one. And hopefully we get off squares. If you didn't select the same number of elements, you might need a mesh, but it's not going to be like rectangular elements, no?
After you get this to your still, with your geometry and surface.
To do what? Mesh, geometry, surface. All right, so now we need to do the roads. Property new, element roads, whatever. Let's put here 0.1, whatever, instead of 1. You can put 1 if you want, I don't know. Roads, okay, we can change that later. So now roads, you activate that one. Let me double check it. Yeah, 1 material. Mesh geometry curve, you can select the 4 edges. Road, click here. Generally, I like to go here, see if that makes sense to the view style and then thickness cross section. See, that's even a lot. So maybe I can go to road property, It doesn't matter if you change it or not. It's just like to make it more realistic, that's all, okay? It should not change much the result. Okay, even that's too big, it doesn't matter. I'll remove this part over here. So I'm gonna go to tools, check, coincident nodes, select all, okay, review, no coincident nodes, okay. I'll create now the boundary conditions, so model, constraint, nodal, can put a title or not. Here we had simply supported, so yesterday for simply supported, what did we select it? 1, 2, and 3. Now for this one, was a roller, no? Is it a roller? So it can move on the Y, 1 and 3. Okay, so that's exactly like yesterday. Model, load, nodal.
Wait, 1 and 3, it should just TX and TZ, right?
Yes, TX and TZ.
Gotcha.
Now we go here to the load, model, load, nodal. And we select that node. What is the load? 95,000. Did you all get to this point? Or did I lose you like halfway? Okay, so you don't need to do this. I do file rebuild, but just because the figure is a little bit more clear, file, save as, BMap summer 2025, oops, A structures. What did I do here? Summer 2025, FEMAP, this will be example 3. Model. As I do this, I do a little prayer. I click the little gear here, create new static, okay, analyze. Then my prayers have been listened. So here we go. I'll close that one. I'll go to the results. Yeah. F5 to the last option here. Oops. Criteria, I guess. And this is what I get.
How did you get that screen?
How did I do what?
Get to
F5. F5 criteria. Then on the deform and contour data, you go here to the last one. I mean, this is exactly the same thing we have been doing the last 3 lectures, so. Okay, so basically now you can go and compare. So what did we get for this problem? We got here about 11,111. So what did we get here on the FEMAP? About 10,000. Here we get about 8. You see, really, this is not really constant. You see, it's changing. But here on the assumption, we say constant is about 8,333. But you see that in real life, this is not really constant. If you want, will be the average value. This one looks like constants. What should we get? About 6250, we get about 64. And this one will be, you see, this one is varying. Should also be the same thing as the top, okay? All right, but you see, really the assumption to say that these two shear flows on the top and the bottom are constant, okay? If it was straight, they will be constant. But since this is not straight, it will be changing, no? So we assume they were constant, but you even see that they're not really constant. But if you want, we have like an average value for these values of 8,333.25. All right. Okay, so let's close this. And let's do one more thing. And I'm not going to start the next example, but since we have, what, about 20 minutes, 25 minutes left, let's do something else. Okay, so 6. Simplify observations about shear flows. Okay, so what type of deformation can a structure encounter? You can find translation, and if you want, rotation. Okay? If you think about dynamics, any object can move in translation or rotation, okay? When a structure can deform in translation or rotation. So if it's defined by translation, generally the equation you're going to be using is summation of force equal to 0 for statics, and if it is rotation, the deformation summation of moments equal to 0. Okay, so something that we have been doing so far, we have been looking at the shear flows due to bending. So one example could be to have a beam subjected to a force, okay, and this will be the cross section. Okay, and for that cross section, we have seen that the sign convention that we have been defining is a constant Q for the shear flows. Okay, but there is another shear flow. So shear flow. So if you want, this will be translation. Translational motion. And for rotational motion, shear flow due to torsion. So in this case, imagine that you have a fixed rod that you apply a torque or a moment. And again, this will be your cross section. In this case, what will be the shear flow? This is the value of your shear flow due to torsion. Okay, and I don't know if you remember, but you did probably derive, we might do it now if we have time. Yes, we have time. What is the expression of the moment for this? You have the moment would be equal to 2 times AQ. Does that equations looks familiar? Okay, so let's say here derivation, since we have time, is easy. So derivation of m equals to AQ. All right, so the important here is the figure. Let's say we have a semicircular structure, center O, point 1, point 2. We're gonna define this as Q12. We're gonna put the radius perpendicular to a point. We're gonna call that distance P. Let's say we apply a moment M over here. And let's say we start the integration from point 1. S, what else do I need to do over here? One more thing, I'm gonna take one little piece of that circular cross section here, and then I'll let you copy it. D8. Okay, so from the figure, what is the area of this triangle? The area of the triangle is base times height divided by 2, no? So what would be the, oops, I forgot to put one more thing here. For the height, this little segment here will be ds. So at the length of our triangle will be P, the height ds, and since this will be the area of this small triangle will be P times ds divided by 2. Now if I just separate the variables, you get 2dA equal PDS. If I integrate, you will find that 2a equal to the integral between 1 and 2 of PDS. Okay, I'm sure you have done that derivation before. Okay, and finally, what we're going to be doing here is that from the figure, we're gonna take the moments about 0.0, positive counterclockwise, so this will give you m minus, okay. What would be the value of the force of the shear flow going from 1 to 2? Will be equal to what? Whatever Q12 is that we assume is constant, it will go through the whole length ds between 1 and 2. So this will be the force, no? Shear flow times distance is the force. What would be the arm? Will be P equal to 0. So this will just give us that M equal to what? Q12 is constant. Integral of PDS between 1 and 2. The one, let's assume over here Q12 constant, even though it's not. And now that what do we have from the previous page? We have that PDS between 1 and 2 is equal to what? 2A. So basically we have what we needed to prove, that M equals to 2A Q12. Okay, and the last thing over here that I'm gonna write down is, so this will be the end for this, is that I'm gonna ask you what is the difference between what is defined as a statically determinate system and what is as something defined as a statically underdeterminate or indeterminate system. So AIF 318, basically, if I needed to give a definition, is a class that deals with statically determinate structures. So does anyone know the difference between statically determinate and statically indeterminate or underdeterminate?
This is when you don't have enough variables to solve.
You're on the right direction. So statically determinate basically means what? Solution can be obtained just using the equilibrium equations, which are what? Summation of forces equal to 0. Summation of moments equal to 0. So in most cases, what does that mean? You have summation of forces on the X, summation of forces on the Y, and then you have summation of moments. Okay? And this will give you 3 unknowns. So what do you think statically indeterminate means? Solution cannot be obtained just from equilibrium equations, summation of forces equal to 0 and summation of moments equal to 0. Let's say here additional equations. I'm going to put here Johnny related to the deformation. Are required. Okay, so basically, what is the big difference? Imagine that you need to build a structure. Let's see just one panel. Is this sufficient for the structure to be stable? Yes, no? So now what happens if I build the same structure? So will this structure be stable over here? I mean, will this break down if you build it? It will not break down, no? Now, what happens if I add one member over here? Yeah, it's gonna be better. But now what happened is that this structure over here actually is adding more unknowns to the equation, no? It's not really needed. So if it's not really needed, the basic equations of equilibrium, okay, this one was already stable, so this one should be able to solve just with summation of forces equal to 0, summation of moments. This one, without the member in the middle, will be the same thing as the top one, but if we add one member, we need more equations to know what's happening over there, no? Because mathematically speaking, what are we doing? We're adding more unknowns. So if you want to be able to solve a system of equations, you need to have the same number of equations as unknowns. Okay? So you need to find additional equations. So this is where we are stopping today. All right?